We've learned in other videos that the atom is in fact made up of even smaller constituent particles, which is pretty amazing because atoms are already unimaginably small. And those particles are the protons, which have positive charge. You have your neutrons, which have neutral charge or no charge. And then you have your electrons, which have negative charge. Now, the big question physicists and chemists were facing over 100 years ago is how are these things configured? And they realized that the positive charge is concentrated at the center of the atom. And in fact, most of the mass, which is made up of the protons and the neutrons, is concentrated at the center. And so an early model for how an atom worked was maybe you have your protons and neutrons in the center. So let's say we're talking about a helium atom. A helium atom has 2 protons in the nucleus, and a typical helium atom would have 2 neutrons as well. So the nucleus might look something like that. And early physicists and chemists said, all right, well, look, the protons have a positive charge, electrons have a negative charge, so they'll be attracted to each other. Opposite signs, opposite charges attract. The same charge repels each other. So maybe the electron, which has a negative charge, orbits around the nucleus the way that a planet would orbit around its star. So maybe it orbits something like this. So maybe one electron has an orbit that looks something like that. And then another electron, if you're talking about a neutral helium atom, would have 2 electrons and 2 protons. Well, maybe the other one orbits something like this. I'm trying to just draw an elliptic or a circular looking orbit. And so this is the idea that the electrons are in orbits. Now, it turns out that this is not exactly the case. Electrons are not in these well-defined circular or elliptical orbits. In fact, at any given point in time, it's not necessarily exactly right there. It could be there, but there's some probability it's here. There's some probability it's there. There's some probability it's there. Some probability it's over there. And so to describe where electrons are likely to be found, physicists and chemists introduced the idea of an orbital. And the best way to think about orbitals is to think about a hydrogen atom. And actually the math for orbitals, its hydrogen is the simplest atom, and so the math for orbitals has been best completed for the hydrogen atom. So in a hydrogen atom, especially the typical isotope of hydrogen found on Earth, the nucleus actually has no neutrons. You just have a single proton at the center. And if you have a neutral hydrogen atom, that one electron, instead of being in orbit around that one proton like that, we can really just think about the probabilities of where it might be. It could be here, it could be here at any given moment, it could be there at any given moment, it could be off the screen at some moment, but it's more likely to be in certain regions of space around the nucleus than others. And we can visualize where it's most likely to be by saying, all right, it looks like 90% of the time it's in a sphere that looks something like that. But once again, it could be here, it could be there, it could be there, it could be there, it could be there, it could be out here, it could be anywhere. We're just saying where it happens to be 90% of the time. That's the visualization. Now, an interesting question is, what if you were to give that electron a little bit more energy? Well, what does energy mean? Well, if you think about planets or a rocket or a satellite orbiting around, if you were to give it a little bit more energy, if you were to give it a little bit push, it could have a larger orbit. It would look something like that. But quantum mechanics isn't about things happening gradually. Sometimes people think quantum means small or something like that. No, it really means that you're talking about discrete packets. So in quantum physics, quantum chemistry, if you add a certain amount of energy to an electron, instead of having a 90% chance of being found in this first shell, this first energy level, it could then be found, it would then jump into the next energy level or the next shell. And so now it might be more 90% of the time it's going to be found in this shell right over here. And then if you were to give it the right boost of energy, once again, just a little bit won't do. You have to give it enough so that it jumps into the next energy level. Then it might form these weird patterns that look kind of like dumbbells, where 90% of the time it's kind of, you can view it as it's on the orbital that looks kind of like that dumbbell shape. And I just did it in kind of the horizontal direction. You could have it in the vertical direction. You could also have it on the in-out direction of this page. And if you're wondering, where do these shapes come from? And if you keep adding more and more energy, you get these more and more exotic shapes for orbitals. Think about standing waves. That's my best hint I can give you. That at the quantum level, or actually at all levels, but especially at the quantum level, you see things like electrons have both particle and wave-like properties. And so imagine something like a standing wave, where if I were to just take a rope, and if I were to just shake it, I might get standing waves that look like that. If I were to take some type of a membrane in 2 dimensions, and if I were to push on one side right here, if I were to drum on that, you might get it so that this part dips down and then that part dips up. And so when you get to 3 dimensions, you end up getting this dumbbell shape when you add more energy, and then you get more and more and more exotic shapes. Just to imagine what some of the first orbitals look like rendered by a computer, you see it right over here. So if you have your lowest energy electron, you are in what is called an s orbital right over here. And this one we would call 1s, because it is at the first shell, the one closest to the nucleus. If you give even more energy, then that electron might jump into the second energy level, or the second shell. And the orbital in that second shell, which would be the default if it's the lowest energy in the second shell, would be the 2s orbital. Once again, you have this spherical orbital. It's just it's more likely to be found further out than when it was just in the 1 shell. And once again, if you add even more energy, you'll still be in the second shell, but you will be into one of these orbitals that have higher energies. So you could view this as the 2p orbital that is in the x dimension. This could be the 2p orbital that is in the y dimension. So some people would call that 2px. Some people would call that 2py. This you could view as the in and out of the page. So you could view that as the z dimension. So that is 2pz. And the orbitals keep going. There is a d orbital once you get to the 3rd shell. Once you get to the 4th shell, there is an f orbital. All we've talked about right now is in hydrogen. If we keep giving more energy to that one electron, what happens to it? What is the shape of the probabilities of where it might be in 3-dimensional space? As you can imagine, if you have 2 electrons, it's not exactly the same, but this is a pretty good approximation. You can actually put 2 electrons in this 1s orbital, but after that, you can imagine the electrons are repelling each other. So another electron doesn't want to go there. And so the 3rd electron that you add is going to end up in the 2s orbital. It's going to be at that higher energy level. And then that can fit too. So you can fit up to 4 electrons between the 1s and then the 2s. And then the 5th one is going to have to go into one of these p orbitals. Now, one last point is to make sure you understand the terminology of orbitals and shells. So first of all, you have this idea of shells, and sometimes the word shell will be used interchangeably with energy level. Energy levels. And so in this diagram, or this visualization right over here, I've depicted the 1 shell, and then I've also depicted the 2 shell. So this is a shell right over here. This is another shell. Now you'll also hear the term subshell, or sometimes people will say sublevels. And that's where they're talking about S or P or D and eventually F. So if I circle this, I'm talking about that first shell. Now the first shell only contains 1 subshell, and that's the 1s subshell. And the 1s subshell only has 1 orbital. Once again, the 1s orbital. So for the first shell, the subshell, and the orbital is all referring to the same thing. But as we get to the second shell, it's a little bit different. If we talk about the subshells, in the second shell, there's S and P. So this is a subshell, and then this is another subshell right over here. There's actually 3 orbitals in the p subshell. So I'll leave you there. In the next video, we'll actually look at various atoms and think about their electron configurations. Where do their electrons sit in which of these shells, subshells, and orbitals?